Hello, this video is a review on sequential logic systems. Here you see a sequential logic system with memory elements and combinational logic circuits. Memory elements stores the current state. Next state is a combinational logic function of current states and input, and output Z is a combinational logic function of the current states Qn if this is a Mealy machine, or Z is a function of Qn and X input if this is a Moore type state machine. We have 4 basic design steps for a sequential logic system. The first step is to draw the state diagram. Second step is to code these states using binary numbers. Third step is to choose the memory element, and then finally designing the combinational circuits to generate output Z and next state Q+. Here you see a bubble diagram with 4 states. The states are shown inside bubbles A, B, C, and D. The state transitions are given with arrows. If this is a Mealy machine, this output is denoted together with the state, or if this is a Mealy machine, if this is a Moore machine, then the output Z is shown on the arrow. The 4 states requires at least 2 bits to be coded. For A, I have chosen 00, for B, 01, for C, 10, and for state D, I have chosen 11. Memory elements can be chosen among many of them. Here are some examples: D, T, or GK type flip-flops, or SR type latch. To design the combinational circuits, we need the truth tables. Here we know the states, we know the next states from the bubble diagram, and we know the transitions for given inputs. For example, when the state is A, if X is 0, next state will be B. Similarly, when the state is A and input is 1, next state will be C. So we can fill in the table for the current states and next states. We can fill the table for the output as well. Then we are adding the state codes. Now I have 2 bits for each state, Q1 and Q0. So when the state is 00 and input is 0, next state will be 01, which denotes the state B. I have chosen D-type flip-flop with this truth table. For a D-type flip-flop, next state will be equal to D, or we can write it as this: D is equal to next state. We need this inverse function because we need to write D1 and D0. For a D-type flip-flop, we can copy Q1 plus to D1 and Q0 plus to D0. And as our last step, we can design the combinational logic for the states. We need to define D1 and D0 as a function of Q1, Q0, and X. So we will write Carnot maps for D1 and D0. Then we can find the function D1 with X, Q1, and Q0.